Hello, for today's lesson we're talking about section 9.2b. We're talking about geometric series in the nth term test for divergence. So a reminder, a geometric series is a series of geometric sequence, and a geometric sequence is where you're multiplying by a constant ratio to get from one term to the next. One thing to note here is we've usually been starting with our first term being at n equals 1, but with a geometric series we typically start at n equals 0. So here's our theorem. Our theorem says a geometric series with a ratio r diverges when the absolute value of r is greater than or equal to 1. And if r is less than 1, then the series converges to the sum, and it gives us the formula for the sum. Now this formula starts at n equals 0. If you started at n equals 1 and you wanted that sum, you would just have to subtract off that first term from this formula. So just make sure you're paying attention to those indices. All right, so let's prove this theorem. So if we look at this theorem, we kind of have three cases. So we have case 1, where r equals plus or minus 1. Then we have case 2, where the absolute value of r is greater than 1. And then we have case 3, where the absolute value of r is less than 1. So we're going to consider case 1 first, and then we'll take a look at case 2 and 3 together. So if r equals plus or minus 1, then my sum is going to just be a plus a plus a to infinity, which means that my partial sums is going to be n times a. Actually, it's going to be n minus 1 times a, because if I think about this, my first partial sum is just going to be a. Oh, yes, it's n times a. My second sum is a plus a, or 2a. Okay, so yes, my nth partial sum is n times a. And if I think about the limit as n goes to infinity of s sub n, which is limit as n goes to infinity of n times a, I am going to get that it is infinity, so it diverges. All right, so now let's consider if r does not equal plus or minus 1. So then, if that's the case, my first partial sum is just a. My second partial sum is going to be a plus ar. And then my third partial sum is going to be a plus ar squared. And my nth partial sum is going to be a, gotta get more space here, plus ar squared plus dot dot dot. And notice that the indice on my partial sum and my exponent are one less. So my last term here is going to be a times r to the n minus 1. And if I multiply both sides by r, then I get r times s sub n equals ar plus ar squared plus ar cubed plus dot 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 plus ar to the n. All right. And so now I'm going to subtract this second equation from the first equation. So I'm going to take s sub n minus r times f sub n. And then what's going to happen is I'm going to get a plus ar squared plus dot 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 plus ar to the n minus 1 minus ar squared plus ar cubed plus dot 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 plus ar to the n minus 1 plus ar to the n. So when I subtract those, I get that s sub n minus r times s sub n is going to equal a minus my last term here, ar to the n, okay, because everything else will cancel. Well, that cancels actually over here. There we go. Okay, so everything cancels. I'm left with the a minus ar to the n. And you might be asking, why is this helpful? So it's helpful because now I can factor out an s sub n on this side, and I get 1 minus r. And then I have a times 1 minus r to the n over here. And then I'm going to divide by that 1 minus r. So now I have s sub n equals a times 1 minus r to the n over 1 minus r. And we want to think about this as our limit as n goes to infinity. So what happens here? As n goes to infinity, so the limit as n goes to infinity of s sub n equals the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. And if r is less than 1, the absolute value of r is less than 1, then we see that what's going to happen is that this piece right here, this r to the n, goes to 0. And so then I get a times 1 on the numerator. And so then I get that that's going to equal a over 1 minus r. Okay? And if the absolute value of r is greater than 1, then that limit as n goes to infinity of a times 1 minus r to the n over 1 minus r will go to infinity, right? So it's going to diverge. Fantastic. All right, so we have that it converges when r is less than 1, and then this is going to be that sum, a over 1 minus r. All right, let's take a look at some examples. Do the following series converge or diverge? Okay, so the first one is the series of 3 over 2 to the n, which we can rewrite it like this. So if we rewrite it like this, we see that we have my a is 3, my r equals 1/2, and then we can identify that this is a geometric series. With r equals 1/2, so we know that r is less than 1. The absolute value of r is less than 1, so it converges. And then we can use our theorem to say that the sum is going to equal a over 1 minus r, which is going to be 3 over 1 minus 1/2, or it's going to be equal to 6. All right. Next example is the geometric series of 3/2 all to the power of n. And so if I write this out, I have 1 over 3/2 over 9/4 over 27/8, so on and so forth. So my a here is 1, and my r is 3/2. And we see that r is greater than 1. The absolute value of r is greater than 1, so it diverges. We don't have to show any work for that because we have a theorem and we already proved it. All right, next. Geometric series with a repeating decimal. So this example is pretty cool. So we want to use the geometric series to write 0.08 repeating as a ratio of 2 integers. So the first thing I'm going to do is I'm going to say, okay, 0.08 repeating is 0.080808, so on and so forth. Okay, so if I take every 2 decimal places, I can write this as 0.08 plus 0.0008 plus 0.0000, see 6 zeros and an 8, plus so on and so forth, okay? So we're kind of dividing it up by 2 decimals, which is every 100th, okay? So then if I'm going to write each of these as a fraction, I get 8 over 10 squared plus 8 over 10 to the 4th plus 8 over 10 to the 6th plus so on and so forth. So then if I want to put that into summation notation, essentially what I'm doing is I have my first term is my a value. Okay, so this is a. And then to get from one term to the next, I'm multiplying by 100th. So I have 8 over 10 squared times 1 over 10 squared to the n. Okay, and you can write those as hundreds instead of 10 squared. It's completely up to you. All right, so my a value is 8 over 10 squared. My r value is 1 over 10 squared. So then I have that this is less than 1. So I can use my geometric series formula to say that the sum, or we know it equal to 0.08 repeating, is going to equal a over 1 minus r, which is 8 over 10 squared divided by 1 minus 100th, which gives me 8/99. So exciting. All right, next thing is just some properties of infinite series. This is just something to have handy. It works exactly like you think it does. All right, so if we have a constant in front of every term, I can pull that constant out. It's basically our distributive property there. If I have a series of sums, I can add each of those individually, and same with subtraction. Okay. Next, we are going to talk about the nth term for divergence. And so here we go. This is very exciting. So our first proof, or our first theorem today, says that if a series converges, then the limit goes to 0 of the terms. The limit of the terms goes to 0. So think about it. If the limit of the terms goes to a constant, even if they're decreasing and it's constantly decreasing and the limit of the terms goes to a constant, I'm always adding a constant. It would be like, always adding a to everything. And that's just not going to work. All right. That just doesn't converge. There's no way to add those up and have the amount I'm adding be insignificant because it's always a constant. So if you want to see the official proof for this, this is in your book. I'm not going to put this one in the video, but you can look in the book. But the theorem we really want to talk about today is this theorem here. That's the nth term test for divergence. So it's basically the logical equivalent of the theorem that says if it converges, then my terms are going to 0. That says if your terms don't go to 0, then it has to diverge. Okay, so if the limit of the terms aren't approaching 0, I know my series can't converge. All right, so let's take a look at some examples here. So these examples say, if possible, use the nth term test to prove divergence. If not possible, explain why. All right, so our first one is we have that the series n equals 0 to infinity of 2 to the n. So let's think about the limit as n goes to infinity of 2 to the n. Well, that equals infinity, so this one diverges. Okay, so my terms are not approaching 0. If I look at b and I look at the limit as n approaches infinity of n factorial over 2n factorial plus 1. So if I look at this, basically that 1 means nothing compared to the factorials. And if I just look at these over here, that limit approaches 1/2. So this equals 1/2, which is not equal to 0, so this diverges. Then the next one, we have 1 over n. And so the limit as n approaches infinity of 1 over n does equal 0. Okay, so we cannot make a conclusion about this. Okay, so we don't know, because our theorem says if the limit of the terms doesn't equal 0, then it diverges. This one, it does equal 0, so we cannot apply the theorem because the if part of the theorem isn't satisfied. Okay, we don't know since limit does not equal 0, or since limit does equal 0, I should say. Since limit is 0. Okay. In fact, this series actually diverges, which we are going to do in a later section. How exciting. All right, one last example. A ball is dropped from a height of 6 feet and begins bouncing as shown. The height of each bounce is 3/4 the height of the previous bounce. Find the total vertical distance traveled by the ball. Okay, so for this one, if we think about this, here's what's happening. And when we want to find the total vertical distance, so let's see here. What is important? We are starting at 6 feet, okay? And every time it is 3/4 the height of the previous bounce. All right, so I am going to start with 6, and then it's going to go up and then down, right? So if I'm going to have my first term is 6, okay, then my next bounce, I have 6, and then to go up, it's going to be 3/4, and then it has to go down, so 3/4. So that's the next bounce, which is going to be 12 times 3/4. Okay, and then my next one, I'm going to do that again. Okay, so I have 6 times 3/4 plus 6 times 3/4 plus, 3/4 squared, excuse me. 3/4 squared and 3/4 squared. And so this bounce here is going to be 12 times 3/4 squared. So that's this bounce from 2 to 3, okay? And so if we continue this pattern, I have 6 plus, so my sum here is going to be 6 plus 12 times 3/4 plus 12 times 3/4 squared plus 12 times 3/4 cubed, so on and so forth. So then if I look at this series here as my geometric series and take the 12 out, so I have 6 plus, and then I'm going to take that constant 12 out, so that comes from those properties. And if I start at n equals 0 to infinity, now because I took the 12 out, the a value is 1, so I have 3/4. And then I want to do n plus 1 here to make sure that my first exponent matches, right? Because we want my first exponent to be 1, so I need to add that 1 so that it matches when n equals 0. So making sure you're paying special attention to all of those indices. And so if I want to then make it so that I can use my formula, I can pull out my a value of 1. N equals 0 to infinity. So now I can write this as 3/4 times 3/4 to the n. Okay, so all I did was peel off that 1 on the inside there. And so then you can say 6 plus 12, and then all of this would be 3/4 times 1 minus r, 1 minus 3/4. So then I am going to have 12 times 3/4 is 9, and then this is a 4th, so reciprocal of 4th is 4. And so then I get 42 feet. How exciting. Okay, go ahead.